Welcome back. All right, this is one a day five, Math 360. So we're going to be going over the exploration and solutions to the problems in this one a day. All right, so for number one, we have f of z is equal to 2 times 1 minus z. This is the PDF, given that z is bounded between 0 and 1. Since we're asked to find the mean of this PDF, or of this distribution and the variance, these are the relationships that we need. To set up the integral for the mean, we're going to set up mu is equal to the integral over the space, so from 0 to 1. I'll use x here as a dummy variable. As we're integrating out over the space, it doesn't matter, but you could use the z as well. That is just strictly notation, so f of x dx. This is going to be the integral from 0 to 1 of x times 2 times 1 minus x dx. And this integral is pretty simple, so I'll calculate this one, but I will do this one using technology. This 2 is being multiplied for everything, so it's a constant with respect to the integral, so I can actually factor that out. And so I get 2 factored out, and then I have 0 to 1. And then I have x times 1, so that's going to give me x, and then just reading the x to the minus x there, it's going to give me minus x squared dx. And then using the linearity of the integral, I can integrate each of these terms individually. And so that's going to give me 2 times the integral of x is going to give me x squared over 2. And the integral of x squared is going to give me x cubed over 3. And I'm going to evaluate that between the endpoints of 0 and 1. Now, it should be obvious, but if not, let me point it out. The upper limit here is the only one that's going to give us any value, as both of these have an x term, and I'm plugging in 0. The lower limit of both of these terms is 0, okay? This is just going to be 2. I'll still plug it in just to kind of show you, but what I mean is factoring out the 1/2, I have 1 squared minus 0 squared. That's the upper limit and lower limit of this first one, minus factoring out the third here, I have 1 cubed minus 0 cubed. Okay, and so again, the lower limit is both 0 on those. So I have, and 1 squared and 1 cubed are also just 1. A really nice property about ones. So this is 2 times, well, this is 1/2 minus 1/3. And I don't know, you can go a couple of ways. You can get a common denominator. I actually just think in this case, it might be easier just to distribute straight across, or distribute the 2 in. So you're going to get 1 minus 2/3. And the reason why that's easy is because if I have a whole that's 3/3, and I subtract 2/3 from it, I'm going to get a remainder of 1/3. So there's the mean, okay, in which I needed to find in order to compute the variance. So I'll set it up the integral and then use technology to actually compute it. So sigma squared is going to equal the integral from 0 to 1. We have x minus our mean, which was 1/3 squared. And then we're going to multiply that by our f of z, or our PDF, which is going to be 2 times 1 minus x. And then we're going to multiply that by dx, okay? Now, if I wanted to calculate this integral out by hand, I could do a couple different things. I think I'd probably do a u sub here, and then plug that u sub value into here. It would just create a little bit neater integral. Otherwise, you could FOIL this out and then multiply each term individually, and then integrate term by term like we did up here. Either way is acceptable, just a little bit more work. Okay, so let me pause here, jump over to the technology, and we'll compute this integral. All right, so let's go ahead and plug in our f of x here. And that's going to be 2 times 1 minus x. Okay, so there's our f of x, and this is in wx maxima. Just playing around with different ideas here. Okay, and then we can compute the, we can say mu is equal to, or is equal to assign a value in or in maxima, you just assign it with a colon. This is going to equal 1/3. Okay. All right, so we have our f of x, we have our mu, and so now let's plug in. So we have integrate, and then we're going to have x minus mu squared times f of x. And we're going to integrate that from x equals 0 to 1. And so when we plug that in, you can see that the value we get out is 1/18th, and so there is our variance. All right, and so from maxima, we saw that the variance then is equal to 1/18th, and so we have then that just gonna summarize, mu is equal to 1/3, and our variance squared, our variance is 1/18. If we wanted to know the standard deviation, we would just take the square root of this term, and that would give us then the standard deviation. Okay, let's jump into problem 2. So I'm going to go ahead and pause this for a second and write that out, and then we'll look at how to do problem 2. All right. For problem 2, it wants us to compute the 3 means. So I'll do one of them, and leave the other 2 for you to try out. So here we have f of u is equal to 3 times 1 minus u. Careful, I thought it was u squared at first. 1 minus u quantity squared. Okay, so we're going to compute the mean, mu, of this. So we're going to compute from 0 to 1. U, my mu's and u's look alike, so be careful there. 3 times 1 minus u squared, quantity squared, du. And so just like before, if I jump over to technology real quick, we'll compute this integral and see what its value is. All right, so we're back here in maxima. And so we have f of mu, or f of u, is equal to 3 times 1 minus u quantity squared. And I want to compute the mean. So let me come up here and say, oh, this is clearing out all the variables, just so we don't get something funky showing up. Oh, my mu's and my u's look like. So we're going to integrate. We have u times 3 times 1 minus u squared. Okay, and then u is going to go from 0 to 1. Okay, and so here we get the value of mu for this f of u is equal to 1/4. So let's jump back over. And you'll see here then that mu is equal to 1/4. And so you're going to compute the other two mu, the other two means with the other two f, or is it w, whatever the function is. There's 2 more functions, so you're going to compute the corresponding means for both of those, and then compare them to the distribution and see if those values make sense. So you're going to try to wrestle through and argue about what you would expect and why does that make sense, or why does it not make sense. Okay. All right, let's jump to, I think it's problem 3. Problem 3 is about using the same PDF from problem 1, and it's actually asking us to look at the quartiles and or these percentiles. The quartiles are special cases of these percentiles. So the 100th percentile is typically what we're talking about there. So the M stands for median, which is the median of the distribution. Normally we're used to discrete sets, where the median would be either the middle number if the set had an odd number, or if the set was even, then it would be the average or the midpoint of the 2 middle sums, or the 2 middle points. In this case, though, since our random variable is continuous, our median will be a point along the interval over which the PDF is defined, and that would be at this pi of 0.5. Okay, so what is this percentile, or how is it defined? I'd like to think of it, or it could be explicitly defined as the area that is bounded by the function, by the PDF, that is to the left of that point P. Okay, so P represents, in this case, the area, and then the pi of P would be the location to the left. So the PDF would go from the integral from -infinity to whatever that point is. Now, our PDF is only defined for 0 to 1, so -infinity would be 0 all the way up until 0. So we would really do our integral from 0 to this point pi p. So to solve all these problems, really, we can just solve it with one equation and then just plug in the numbers for any specific case that we are curious about. So let's go ahead and do that. And then I'll let you do the computations to find the actual values. Okay, so again, just to kind of think about, I'm going to draw a generic kind of bell-shaped curve looking PDF. This is not our PDF, but just to kind of give you a sense. So imagine that this is our PDF, right? And so our x-axis runs along the horizontal here. And so the integral from negative infinity, so all this shaded region, so to whatever value you're looking for, let's say we're looking at this part right here. So this is the location of pi p, which is going to equal the bounded area to the left, that is bounded by our PDF here. So all this area to the left here, that is the value of phi. And so when this location equals this bounded area, we found that percentile. And that's what we're looking for, okay? So let's go ahead and plug in our PDF and evaluate for some generic p. So we have p is equal to the integral. Now, again, our PDF is only defined for when x is, or z in our case, is greater than or equal to 0. So anything below that is going to be 0. So we don't really need to. And we're going to integrate to pi to some generic pi p. And that's actually what we're going to be solving for. For our integral, it's going to be 1 minus z dz. Okay. So if we pull out that 2, and then we look at the integral from 0 to pi p, we have 1 minus z dz. Integrating that, we get 2 times, we get z minus z squared over 2, evaluated from 0 to pi p. Okay, and that's going to, again, equal our p-value here. Okay, now I can distribute through with the 2, or I can divide by 2 on both sides. And then again, notice that the bottom limit of integration here doesn't play any effect on our value. So minus, it says it's going to be minus 0 for the lower one. So I just need to plug in pi p directly, and I'm going to divide that by 2. So I get p over 2 is equal to pi p minus 1/2 pi squared p. Okay, and so I don't know if it's easier to multiply by 2, actually. We kind of have that coefficient of 2 here. Yeah, let me multiply everything through by 2. So I'm going to get p is equal to 2 pi p minus pi p squared. Okay, and so now to solve this, remember this is the variable we're after is pi p here. So I'm going to set this equal to 0, and I'm going to get 0 is equal to, and I'm going to subtract that p over plus 2 pi p minus pi p squared. Now notice it's a quadratic in pi p, so that's our value. So I can use the quadratic formula. This pi p is equal to opposite of b, so negative 2 pi b, plus or minus the square root of, it's going to be 4 pi p squared. Oh, sorry, no, not 4 pi, that's the variable. 4. I was wondering why that looks so funky. So this is negative 2. This is a positive 2 here, that looks like a negative. This is minus 2 plus or minus square root of 4 minus, let's see, we have a negative 4 times negative p plus times a negative 1 here, all over 2 times a negative 1. Okay. So I guess we'll just finish it up. So it's just negative 2 plus or minus the square root of, notice that there's a 4 in common here, so I can factor that out. And then I have, it's going to give me what, a 1 minus p, it looks like. 1 minus p, all divided by a negative 2. Okay, and then this is square root of 4, so that's a 2. So I can factor out, and that 2, this 2, and this 2 are all going to cancel, so I'm left with a negative 1 plus or minus, and actually that negative can absorb, and that makes it a positive, and that just switches the sign to negative positive. And then I have the square root of 1 minus p. Okay. All right. So to find any p-value, I just need to plug it into 1 minus plus the square root of 1 minus p, and that will give me the desired p-values. That will give me the corresponding values that I'm looking for here. Okay. All right. I hope that was helpful. And let's jump into, I think that was all for number 3. Let's look at number 4. In our last problem here, number 4, we have 9 observations of some data, and these are the 9 observations here. And we want to know if it's a good match for the PDF given earlier, which is f of, I'm using x now, but it was from z, 2x, from 0 to 1. Okay, so we're going to jump over to some technology here and utilize that to consider whether or not this is a good fit. I went ahead and inputted the data into the spreadsheet version of GeoGebra. And then if I highlight all these values, I'm going to go ahead and create a list. And I'm doing this because I want to sort them. Now, I've already created the list, but if I did that, it's going to be called L1. And so when I do that, that creates this list here. So that's L1. And with L1, I want to sort L1. And so now I have the values from least to greatest, which is exactly what I was looking for. Okay, and so we're going to use these values here. These are going to be our marks along the way. GeoGebra has a function called random, which is going to pull from a random distribution, which is the same as a uniform distribution on the interval from 0 to 1. We're going to pull that, but we're going to multiply it by 2 because that's our PDF. Okay, and so we're going to go ahead and pull this down for the same 9 values. And then we're going to take these values and we're going to create a list of these as well. And there it is, L3. And then now I want to sort to these values as well. So sort L3. That creates my list L4. Okay, and now to create the QQ plot, I'm going to show that plot's going to pop up over here. I'm going to use the zip function, and I'm going to create an order pair of P comma Q. These are just temporary variables, the dummy variables. And so the way you put them in is the order in which you want them, and then the list that you're pulling from. So we're going to pull from L1. Sorry, I should name the variable first, and then where it's coming from. So L1, and then Q, and we're going to pull that from L. Oh, sorry, not L1. That should be L2. And then we're going to pull from Q, and this should be L4. Okay. And so there is our QQ plot. And the next thing we want to do is put a polyline through that. So line and best fit. So fit poly. And we're going to do L5, and we want it to be linear. Okay. And so as you look at this value, you see that they're lining up pretty well along that line, which is a really good indicator. Now, they're not exactly through them, obviously, but you can see that they're definitely trending in that value, and they're getting pretty close. So with only 9 observations, it's hard to make a for sure guess or estimate, but this does give some pretty compelling evidence that it might be. One more thing to look at is let's consider the summary using a one variable analysis here in GeoGebra. We can look at the statistics of this, and we see that the mean is 0.6644, and the standard deviation is 0.2429. Well, from earlier, we saw that the mean was 2/3. So 2/3 numerically is 0.6667. So that's really close. And then our sample mean is, our sample standard deviation is 0.2576. And our standard deviation was 1 over the square root of 18, which was 0.2357. So again, very, very close to the exact value that we're seeing here. So it does seem like a reasonable approximation based on the sample and standard deviations, the sample mean and the sample standard deviation being very close to the statistical values of the distribution from the mean and the standard deviation, combined with the evidence from the QQ plot following along that line. You can see that they're pretty closely lining up. So that does seem to compel that it is the fact that the sample was coming from this distribution. Okay. All right. I hope that was helpful. That kind of gives you an idea of how to tackle each of the problems here in 185. And I look forward to seeing you in the next video.